Hi, I'm Nicole Melso, and I'm a sixth-year grad student at Columbia University, working with David Shimonovich. Today, I'd like to tell you about an instrument that we've recently commissioned last year called the Circumgalactic H-alpha Spectrograph, or CHaS. Let me just see if I can move forward. Okay. It won't let me advance for some reason. There we go. Okay, so CHaS is a narrowband, moderate resolution, wide field IFU spectrograph. And it was originally optimized to work at the H-alpha wavelength, which is namesake emission, but we've actually optimized it now to work at a broad range of optical emission lines, anywhere between 400 to 900 nanometers, but it observes one of these emission lines at a time, so it has a very narrow band filter of 30 angstroms. And we're using CHaS to target low redshift galaxies, a redshift of less than 0.01, where the CGM would fill the 10 by 10 arc minute field of view. And we can resolve structures on the order of 1 to 5 kiloparsecs at this resolution of a few arc seconds. And we have a velocity resolution of 15 to 30 kilometers per second. And then the last goal is that we're targeting faint emission from the CGM on the order of 1 to 10 millirelli. So well, let me just also tell you about the instrument real quick. So this is the image of a model of CHaS, and then you can see us installing it at a few different stages at MDM Observatory on Kitt Peak. And so how do we reach these sensitivities, this 1 to 10 millirelli? So let me just tell you a little bit about some features of CHaS. So like I said, it's installed on the 2.4 meter. And so it's an IFU spectrograph that's paired with a smaller aperture telescope, which is nice because that gives us a wide field of view, which gives us a large light collecting power. So here I've plotted the grasp versus the resolving power. And you can see that CHaS occupies this space up here where we have a large light collecting power and a moderate spectral resolution of 10 to 20,000. We actually have 2 resolution modes, which are these 2 CHaS points here. And this makes CHaS a competitive survey instrument, plotted on here with many excellent existing and proposed IFU spectrographs. And the other thing that's nice about having it on the 2.4 meter telescope is that it's a smaller observatory with a lot of student involvement, which has been great for me. And I've included some pictures of us having a lot of fun at the observatory. That's our van. So then how does CHaS work? It's fed by a microlens without fibers. It's just the microlens, and it has 60,000 lenslets that collect a spectral image without the need to scan. So if you have the microlens array with the spectrograph optics, no grading, you get this pointillism image of your target. So you see this is some early observations we took of Jupiter and Saturn. And then if you install the grading, you disperse the image of each lenslet into a spectrum. So here's the ring nebula with a wide filter. So no narrowband filter here. But we don't want to take images that have these long spectra that have overlapping features. So we install that narrowband 30 angstrom filter at the front of the instrument, and that gives us something more like this, where you can see that the stars, each lenslet that's over a star creates a continuum spectrum, but then the discrete emission from the crab here creates these an image of each lenslet where the position of that emission line is offset in the spectral direction. So this image is actually a cube because it has the position of the emission line in the spectral direction that gives you the velocity. And so in this way, we can use a single exposure to take a cube image that doesn't require us to scan. And we can stack these up to improve the signal of noise. And I've shown you on the right here, this is our detectable flux versus an angular extent. And so it's very difficult to get the signal to noise in the range of 1 to 10 millirelli with just in every single lenslet. And so we can bin these lenslets together. We have a very good filling factor, so we can bin them up. And instead of taking something like 100 hours to reach this, we could reach this 1 to 10 millirelli region within maybe 10 hours at an angular or at a physical size of something like 10 kiloparsecs. And then just lastly, I'd like to show you some of the data that we took. We started our science run in March, and this is a CHaS image on the bottom of the whale galaxy, NGC 4631. And then on the top, I've created the first velocity map from CHaS which is, you can see that every single lenslet has a velocity measurement, and this is just focusing on the bright emission in the disk. And we have some, this is a relative velocity with respect to the halo gas H1 cube. And you see there's some features like this, this interesting bubble feature that is also in the radio cube, but is seen here in relative velocity, and then some gradient and possibly turbulent structures that we're looking into with CHaS. So we're excited to go back to the mountain and extend this into the fainter gas, this map into the fainter gas beyond the disk. So thanks, and I'll take any questions.
Awesome, thanks, Nicole. Carlos says these results look awesome in the chat. Does anyone have a question for Nicole? I'm curious what the plans are in terms of, like, are you planning a large survey of other galaxies, or what's the plan for the spectrograph overall?
So yeah, we have a couple of targets picked out for maybe 10 to 100 hour exposures. So our first science run will just be building up maybe five or six targets with very long exposures that will turn into these velocity maps. But in the future, it's commissioned at MDM, so it's Ohio State, Columbia, Michigan, Dartmouth. So it'll be an observatory instrument that can be used.
Perfect. That's wonderful. Thank you so much.